Dear friends, welcome to this special webinar being held on Earth Day in the framework of the French presidency of the European Council. I'm very pleased to open this webinar, which has been organized by the Office of Science and Technology and the Cultural Office of the French Consulate in close collaboration with other EU consulates in Boston. Let me acknowledge the participation today of my colleagues and friends, Nicole Metzenbach at the German Consul General, Stratos Eftimiou, the Consul General of Greece, and Federica Sereni, our Italian colleague. It has been a pleasure working hand in hand our teams to prepare this today. For this special Earth Day event on April 22nd, we propose to have some views on one of the most visible aspects of climate change, rising sea levels and coastal erosion. Both have major consequences on our environment, our cities, our citizens, and what has been done and what should have been done, what should be done to prevent flooding of cities along the coast. Here are the questions often asked by the public. The latest report of the United Nations Intergovernmental Panel on Climate Change, published in February 2022, shows already rising temperatures approaching the 1.52 degrees Celsius increase, which was fixed as a limit by the Paris Climate Agreement. This report predicts also dramatic effects of climate change throughout the world on oceans and coastal ecosystems. The EU is alarmed by this situation and has taken bold decision to curb its own carbon emissions and mobilize efforts throughout the world. For instance, France has one of the lowest levels of carbon emissions within the EU and will continue on this path with massive investments in nuclear energy, solar and offshore wind, as well as hydrogen and energy sufficient solutions. But we need non-EU countries to live up to their commitments and to step up their climate action. That's why it's great to have this exchange today between specialists of New England and European specialists. New England's coastal erosion is now a major concern with more and more flooding days, more frequent storms. In Massachusetts, the sea level off the coast is 8 inches higher than it was in 1950, and it has significantly accelerated in recent years, now rising about 1 inch every year, according to the NOAA. European countries also face similar effect of rising sea levels and coastal erosion. Today, we have invited a panel of 4 European experts in this field and Professor Jerry Mitrovica from the Harvard Science Department. Professor, thank you very much for moderating today's exchanges. Professor Jerry Mitrovica is the Frank D. Baird Junior Professor of Science in the Department of Earth and Planetary Sciences at Harvard since 2009, after 16 years as a professor of physics at the University of Toronto. His work involves computer modeling of sea level changes in both the geological past and in the modern world. His group's research deals with analysis of land and satellite-based record of sea level change over the last decades and the coastal hazards that face humanity in the 21st century. Another part of his work is about modeling the unique geometry of sea level changes associated with melting ice sheets and glaciers as a method of detailing changes in the stability of polar ice sheets. So we have 4 great panelists for this webinar. They come from different countries of the EU. We'll let Professor Mitrovica introduce them. Thank you very much for your attention. Let's stand together and address today's challenges with science and political will. Thank you.
Okay, well, thank you very much to the Consul General for this kind introduction and for the invitation to moderate this important webinar today. And thank you to all at the Consulate who helped to organize the event. You know, a well-known politician in Boston, Tip O'Neill, he was a former Speaker of the US House of Representatives, once said, and he's often quoted for this, that all politics is local. So I'll borrow from him today to say that all sea level rise and its impacts on coastal environments are local. As we'll see today, risks, resilience, and impacts to coastal communities across the globe from human-induced sea level rise will be vastly different, whether we're considering Boston, Brittany, Kiel, Genoa, Athens, etc. And this complexity in sea level rise is a major obstacle to designing adaptation strategies, obstacles, as we'll also hear today, that involve important socioeconomic, scientific, political, and even ethical considerations. But what choice do we have in this? We have no choice. Dealing with this man-made problem is a moral imperative for us all. I'd like to start today by just showing work by my group at Harvard University that speaks to one very specific complexity in the story of global warming and sea level change. It's going to be a simple quiz that I hope will illustrate the scientific nuances in our understanding of sea level change. Let me share my screen. You can let me know if you see this or not. Here's a map of Europe. What would sea level rise be across these coastal environments? Let me begin by focusing a little bit on France, our host today, the French consulate, and ask a simple quiz for all of those on this webinar that might be somewhat surprising to you. Let me ask you, what would sea level rise be in Normandy here in Caen, and Brittany there in Brest, if enough ice from Greenland melted to raise global average sea level 1 meter? What would we see at these two French locations that are facing unprecedented flooding and coastal hazard? So the question, to rephrase it, is if we melted enough ice from Greenland that if the Earth was a bathtub and sea level went up 1 meter on average around the globe, what would we actually see at these sites? Cursor. We would actually see about 1/3 of a meter. For those on the west side of the Atlantic, this means about 1 foot of sea level change. So we would see much less than the global average in this case if the Greenland ice sheet were melting. But now let me ask you, what would we see at these same two sites if enough ice from the Antarctic melted to raise global average sea level? What would that answer be? Would it be 1/3 of a meter? No, the answer would be about 1.2 meters, or again, for those on the other side, on my side of the Atlantic today, that is about 4 feet of sea level change. Right? What is the reasoning behind this? One of our speakers will discuss a spectrum of different causes of this variability, but I'm going to talk to you about one specific one that is highly counterintuitive, but has been known for decades in the scientific literature. I'll illustrate it with this simple image here. An ice sheet, just like the sun and the moon, exerts a gravitational pull on water around it. When that ice sheet melts, so it moves from this dashed line to this inner red line, a number of things happen. The first thing is, of course, you're dumping all of this water from melted ice into the ocean. But the second, somewhat counterintuitive aspect of this is that the gravitational pull of the ice sheet on the water decreases because the ice sheet is shrinking, and water will move away from that ice sheet. And it turns out, close to the ice sheet, sea level will actually fall. It's one of the most counterintuitive results in all of climate change, that sea level rise near an ice sheet that melts will actually be a sea level fall. I should have said sea level change near an ice sheet that melts would be a sea level fall. This is about one aspect of the kind of geographic variability in sea level that scientists know about and we model. But it also indicates to you, as I was suggesting earlier, that all sea level is local. The adaptation strategies in Normandy will have to be different, believe it or not, because from the adaptation strategies in Brest. There will be local conditions that govern those adaptation strategies. And it's important for us to remember. And it's important in a pressing way, because as a sea level scientist, I'm often asked to comment on articles like this that appear in our newspapers. Sea level rise is affecting almost the entire French coastal region. Right? It is particularly dramatic in Normandy. I've been asked probably on a dozen occasions to talk about coastal erosion in Normandy. And let me, just for the sake of driving this point home, show you, get out of this thing, and show you a YouTube clip I found last night of what happened in Normandy about 10 years ago on one of the cliffs. This is an ongoing process of cliff erosion that is occurring in Normandy. This erosion is not only associated with the sea level rise and sea level changes I will talk about, it's also associated with storms, it's associated with changes in global ocean circulation, tides, and etc. And it's a pressing, as I said, moral imperative. Now, we're lucky today to have 4 speakers who will discuss a range of aspects of this problem. I guess perhaps I should say, just for the sake of organization, that the plan is for each of our speakers to speak for about 15 minutes. I will look at the chat during the whole process. And if there are questions specific to those speakers, I will perhaps take 2 or 3 of them to ask at the end of each of their talk. But one important aspect of this event that's been set up by the consulate is that we also want to save time at the end for a group discussion where all our panelists can come together to discuss more pressing global and local issues as we face this incredible detrimental change in Earth's climate. So let me start by introducing, and I'll stop sharing as well, if I can find my cursor. Let me start by discussing or introducing our first speaker today, was Davide, Salas, and Melina. He'll be speaking to us not only about what I talked to you about, but something that is also very close to my heart, the many factors that give rise to variability in sea level change, not just the ones I've talked about, from place to place, and the satellite observations of this variability. David is a climate scientist at the Centre National de Recherche Météorologique, that is, for those of us on the Boston side of the Atlantic, the National Center for Meteorological Research in Toulouse. His main research objective is to better understand and estimate past and future climate change through the use of sophisticated climate modeling. David, the stage is all yours.
Thank you very much, Jerry, for the introduction. So I'll share my screen. There. Okay, so yes, I'll say a few words about observed and projected modeled global and regional sea level rise. But at first, I will introduce 2 notions, those of absolute or geocentric sea level, for example, sea level observed from space relative to the center of the Earth, and another notion which is relative sea level rise. Until the satellite era, altimetry era, sea level rise could be observed from tide gauges, which are tied to the ground. And so tide gauges measure sea level which is relative to the ground because the ground moves vertically. And so I say a few words about observations about past and recent sea level changes. And so first, why does sea level vary? There are 2 reasons, 2 main reasons. First, due to ocean density changes. Since if oceans are warming, water is expanding, and the other way, if oceans are cooling, water is shrinking. The other aspect is that there can be ocean mass variations due to water exchanges between the oceans and other components of the climate system. For example, the melting of glaciers everywhere in the Rocky Mountains, in the Alps, Ice sheets. Jerry gave us the example of the melting of Greenland or the Antarctica. Also, this is perhaps a bit less obvious, but there are also changes in sea level due to land water storage changes. If, for example, if there is a lot of water at some time in some area of the world, there can be some part of this water that goes. It can be temporary to the ocean, increasing sea level. And also something which is much smaller. Since the atmosphere currently is warming, it can contain more water vapor, and this water vapor is actually taken from the ocean. And so when one says that the sea level has increased by about 20 centimeters since 1900, there is a frequently asked question. Some people can tell you that, for example, 20 or 18,000 years before now, the sea level was about 120 to 130 meters less than it is today. So actually, why care for just 20 centimeters? So sea level has always varied, especially here I show part of the Quaternary era over the last 800,000 years. And so you can see variations. The vertical axis is in meters. And you see that the sea level can be about 130 meters less than it is now when the climate is cold, for example, during the end of the last ice age. But it can be also higher than it is now. For example, an estimate of between 6 and 10 meters during the last interglacial, which was about 125,000 years before present. So sea level has been observed over a few centuries already, because there are long tide gauge time series, especially, for example, in La Rochelle, more than 300 years, and other areas also in Brest. So tide gauges with, of course, by definition, oops, sorry. Oops, I killed my presentation. Can you see it again? Yes?
Yes.
Yes.
Yes, okay. So I come back to the presentation. I did something wrong. So by definition, of course, tide gauges are at the coast, but now, since 1993, we have satellite altimetry, which offers a global coverage, nearly global. And so it's possible to observe very precisely global sea level, but also regional sea level change structures. And since 1993, the sea level increase is now about 9 to 10 centimeters, plus 3.5 millimeters per year on average over that time period. You have the whole curve here. With variations, it's not completely linear. There is a bit of accelerations during the most recent years. And also you can see some years where the trend is increasing or decreasing, due especially to El Nino, La Nina phenomena. So this is a curve about global mean sea level, but there are there are structures in that sea level. You can see here on this map that in some areas the mean sea level trend can be up to 10 millimeters per year in some areas, but in other areas the trend is very small. So this is well explained now. This shows the global mean sea level budget since 1971. You can see there are several parts here. There is the part which is due to the warming of the ocean down to 700 meters, the part between 700 and 2,000 meters, and the deeper ocean contribution. All of those here The ice also contributes, and so you have the biggest contribution is from the glaciers and also Greenland, and the contribution of Antarctica is a bit smaller. And also there is a contribution of land water storage changes that you can see here. When we add up all these contributions measured independently from satellite altimetry, so we get to the red bar, and you see that it's nearly compatible with what is observed. That's the dashed curve directly observed with satellites. Here I provide an example. This is a paper, a very good recent paper, which shows here first on the map, which is at the top, for the period 1993-2018, two things. So first, the tide gauge measurements. So let's, for example, focus on the eastern coast of the US. You can see that there are, in some areas, the sea level increases by 5 millimeters per year. And you see that it can be quite different what is observed at the coast. So relative sea level, it can be quite different from what is observed by altimetry. So this is the colored areas on the ocean. And so they did some work trying, and they succeeded actually to decompose the observed sea level at the coast to split that up into different contributions. First, there is the water mass redistribution with the contributions of the ice melting from glaciers and ice sheets and other liquid water transfers. So that's the map I'm showing here. Water mass redistribution. A big part of the spatial variability is due to ocean dynamics and density, due to the variability of ocean circulation, ocean currents, and also it creates differences in density, and it creates spatial structures, as you can see here on that part. And there is also something to the right. You have contributions due to vertical land movements that can be decomposed in two parts: the glacial isostatic adjustment, because there was an ice sheet in the north of North America, as you know. And so in that area that's in red, you can see that the ground is rising. And further south, so for example, in the region of Boston, you can see that Boston is kind of at the limit between the two domains, but further south, you see that we are in blue, and so the ground is sinking. But there are also other land movements, and for different reasons. For example, due to coastal water pumping, for example, there can be significant sinking of the land near the coast. And so adding up all this, in most cases, it's possible to explain what is directly observed by tide gauges. And so future projections quite rapidly. So since we understood what happened in the past on the 1971-2018 period, the work that is done by climate scientists and different communities is to project the contribution of every component to future sea level rise. So it's necessary to know how much all the glaciers around the world are going to melt, hence contributing to sea level rise, how the Greenland or Antarctic ice sheet may melt, how the oceans are going to warm. So we get that collection of curves for different scenarios. So you see that some curves are relatively low, but all curves show you that actually the sea level will go on increasing. Global sea level will go on increasing anyway during the decades and centuries to come. about 30 to 40 centimeters for the most optimistic scenario, the SSP 1.9, which is a scenario with very large emission cuts in greenhouse gases. On the contrary, if we are considering more pessimistic scenarios like the SSP 3.7 or SSP 5 8.5, where greenhouse gas emissions increase a lot, we might have up to, according to the shaded area, about 1 meter sea level increase, global mean, but more sea level increase cannot be ruled out, 1.5 and up to 2 meters for 2100. And the long-term sea level rise, it's important to stress that even if temperature, the change in temperature, global mean temperature, with respect to the pre-industrial is contained to 1.5, sea level will continue to increase up to 2-3 meters. Even in that case, it can be more, 2 to 6 meters if warming is limited to 2 degrees. And of course, it's much more if the warming is as much as 5 degrees sustained for 2000 years, as you can see, about 20 meters. Of course, in the future, sea level rise also displays regional structures. Again, under the low greenhouse gas emissions, the sea level rise is less than in the emission scenario with very high greenhouse gas emissions. And so you see that there are regional structures, especially on the something that is quite prominent on these two pictures is that the eastern coast of the US sees enhanced sea level rise compared to the rest of the planet for the reasons I detailed previously in the observations. And so finally, my last slide, it's important to stress that whatever the means we have or the political context, observations should be sustained for further analysis and to monitor how the sea level increases. Also, modeling is of course necessary to try and estimate future sea level from scales ranging to very local to global. These projections still need to be improved. Old components, especially ice sheets, since ice sheets will be the dominant contributors to future sea level rise. But also, and I will stop here, it's really necessary to better share data and practices. Personally, I've seen that there are many data sets, but for users, it's really difficult to know how to use this data, how to for action. And so first, the data should be better shared, better accessible, and it's necessary to go into climate action to counter sea level rise or to limit sea level rise and its effects. It's necessary to co-design climate services together with practitioners, stakeholders, and scientists to better adapt to the dangers of rising sea levels. Thank you.
Thank you, David. Again, if you have any questions, please just write them in the chat and I can transmit them to David. I have a question, several in fact. One is, even within the individual scenarios, you talk about low, medium, and high emission scenarios, there is uncertainty in the projection. And what, from a physical point of view, gives rise to that? And so what are the major areas of uncertainty? And why is it that your slide also showed some rather extreme projections? What is it in those scenarios that is not taken into account in the projections that show lower sea level change?
Thank you for your question. There are uncertainties in projecting the contribution of every component. Some uncertainties are bigger than others. For example, just considering an emission, greenhouse gas emission scenario, and putting that in one or even many more models, like 50 models, about 50 models, like for the ones the IPCC is considering. Even doing that, there are very different warmings of the ocean simulated by the models, and so there is uncertainty there. But I would say that, well, this can be improved. There is a lot of work to do, but there are also missing components in climate models, like interactive ice sheets. There are processes that were completely missing. Well, the contribution of ice sheets may be very, very big for the future, but in case, for example, the West Antarctic collapses, but this is still unknown and very, very badly constrained at the moment, because these ice sheet models are just not currently in the climate models. So we do separated simulations. We add up all figures without considering the feedbacks between these different components. And so I think that a big area of research, and but this is true for other components as well. Even if other components are better constrained, like for example glaciers, there is a limit of water in glaciers, much more limited than in the Greenland and Antarctic ice sheets. So,
yeah. What would be your prognosis for projections, not of global average sea level, but one of the take-home messages of your talk is, of course, the geographic variability. What are the steps or obstacles to accurate regional projections to 2100, for example?
Well, I studied myself regional structures of just thermal expansion in Météo-France's model and in other models. So there are things that models can do very, very well, like for example, variability in the Pacific. The structures were quite nice, but in other regions, well, honestly, we did quite wrong, especially around the Antarctic. So there is still some work to do in oceanography. I would say probably, so there is a trend towards this, but probably working at a higher resolution could be a key to the problem, because there are things we know that cannot be well resolved in the current generation of climate models, those used by the IPCC, for example, especially in the Atlantic, where the Gulf Stream is not well simulated. So yes, so there is still some work to do in the models themselves, and also in new couplings that should be added to these models to better simulate. But that's only one part of the problem. That's the climate part. There is also some work to do, of course, for example, to better assess land movements. That's for the monitoring part. This is so observations are also both are really necessary.
Thank you, David. Thank you very much. Let's move to our second speaker now, David Bonaldo. David is a research scientist at the Institute of Marine Sciences and of the National Research Council in Venice, Italy. And if there is an area we all think about in the context of sea level rise, one of them is Venice, Italy. He has a broad range of skills, including climate modeling, as we've just heard, of atmosphere and ocean interactions. And his doctoral work at the University of Padua also gave him insights into coastal environments and the impacts on coastal environments like estuaries and lagoons of both man-made and natural impacts of sea level rise. David, please begin.
So, thank you very much for introducing me, and good morning or good afternoon, depending on where we are, to everyone. Now I share my screen, and in the next few minutes, I would like to say something about the present threats affecting the Italian coast. And by the way, do you see my presentation? Okay, great. Present threats affecting the Italian coastal systems, as well as how scientific research and technology and management strategies are striving to cope with them. And we will find out that even in the uniqueness lie some germs of global challenges. Now, coastal erosion is the process that occurs when a stretch of coast, when the factors favoring the supply or the trapping of sediments are not sufficient to contrast the effect of the ones that cause sediment removal, combined with the relative rise of the sea level. And in Italy, this process is deeply entangled within our lives. We can see it in action, for instance, every time we decide to go back to that nice restaurant in front of the sea, where we had dinner a few years ago, and discover that it is now actually over the sea. And now, while the owner of this restaurant in Sicily keeps heroically holding his ground against the rising sea, even traveling along the coast might be something somewhat uncertain, as long tracts of our coastal infrastructures are actually very exposed to the action of the sea. And also, our cultural treasures testify what is going on. Piscine, where artificial ponds where fish were grown, were built during the Roman age along the coast, with very precise constructive criteria to allow the hydraulic regulation of the exchanges of water between the basin and the sea. And the Roman coast is studded with this kind of structures that are visible also from satellite images. And since their function is very well known, they can be used, and they are used, as a marker for sea level, and of course, by comparison, for a relative sea level rise over the millennial timescale. But we can also jump some hundreds of kilometers north and some centuries ahead and land in Venice in the 18th century. And in that period, painters such as Canaletto and many others, thanks to the use of the so-called camera oscura, were able to take the closest thing to a photograph that you could ever achieve without actually having a camera. And they basically depicted every spot of Venice. So now you can have some fun finding the difference between what they depicted 250 years ago and what you can see today. And we could take, for instance, this picture here, which you can find in Washington. Okay, it's not Boston, but it's still closer to Boston than Venice. At the National Gallery of Art by Francesco Guardi, depicting the Ponte dei Tre Archi as it was in 1770 and compared it with what you could see now. As you see, the water level is several tens of centimeters higher now, about approximately 30 centimeters. And in a city like Venice, the price of this apparently small span is actually very high. Now, present estimates suggest that at national level, erosion affects more than 1,600 kilometers of the Italian coast, which means around 40% of the low-lying coast. But in order to really quantify the risk that affect our coastal areas, we also have to consider the geographical and socioeconomic structure of the mainland. Approximately 70% of Italian population lives or works within 10 kilometers of the coast, and large zones of the coastal territory are actually coastal plains, which means that they lie at a height which is very close to the sea level, and sometimes even lower, such as large land reclamated areas in eastern Veneto or in Lazio. And these coastal plains are also often densely populated and crossed by important infrastructures. And it is important to know that colleagues from ENEA, which is the National Agency for Sustainability, have been mapping these systems for years and ended up pointing out that more than 5,600 square kilometers of Italian coastal territory is actually below the possible sea level expected for the end of the century in the most severe scenario. This doesn't mean that they are automatically destined to be flooded, even in that case, but still it means that we have to pay attention and take care to a territory which is overall as large as the whole Liguria region. Now, to be honest, a significant fraction of this number are more or less directly related with anthropogenic factors. massive damming and gravel and sand mining on river basins, particularly in the first half of the 20th century, have dramatically decreased the amount of sediment actually reaching the sea and becoming available for the coast. And the disruption of long tracts of coastal dunes, mostly due to heavy touristic exploitation, have deprived the coast of its natural sediment reservoir, which used to enable them to compensate the seasonal erosional and depositional cycle through winter and summer. And also, coastal protection strategies, sometimes excessively oriented toward hard solution, often proved unsuccessful, as they were actually limiting the system's capability to retain some important morphodynamic processes and the capability to self-adjust in a way to the ongoing changes, and that ended up squeezing the coast between a rigid shoreline and the rising sea. So, if on the one hand we are paying the price of a number of wrong choices, on the other hand, several efforts have been carried out mostly in recent years in order to enhance our capability to respond to this increasing pressure. And to this aim, a lot has been done toward reducing the fragmentation among the subjects involved in coastal resilience. At the national level, this has been done by gathering, for instance, the Italian universities and research institutions into large framework projects that were actually capable of putting together and consolidating the scientific community and funnel their efforts and focus them. Then, from the administrative point of view, in order to create an overarching framework for coastal management, which in Italy is largely upon regional administrations, in 2016, the Ministry for Environment created the National Panel on Coastal Erosion, which is Tavolo Nazionale sull'Erosione Costiera in Italian, putting together regional and national institutions under a coordinated framework with some support from the scientific network. And on both scientific and administrative fronts, this kind of effort has been upscaled at the transnational policy level with an intensive participation in cross-border cooperation programs and other initiatives. Although true it is that, as Jerry Mitrovica pointed out, adaptation is to some extent, at least, ultimately local. But anyway, one initiative in which our institute is directly involved at this international level is this Danubius RI, which is a new distributed pan-European research infrastructure for the study of the river-sea system. And now this research infrastructure is in its implementation phase, but it's foreseen to reach the operational phase in 2024. One key aspect for increasing the resilience of our coastal systems is to improve our capability to predict metocean processes in particular and their impacts on the coast. On time scales that can range from a few hours and days up to the climate scale. And as ever more powerful computers become available, it becomes easier for us to implement numerical models, solving the equations underlying the physical processes we want to describe, and have reliable predictions at a very high spatial detail, like this one in this animation, and potentially for long periods of time. So we can give increasingly accurate predictions of the high tide that could hit Venice in the next 48 hours, or we can investigate the future wave climate in a climate change scenario. And in both these fronts, promising perspectives are coming from machine learning techniques that can help or even substitute numerical models in this task at a very low computational cost than the prices that they are blind to the physics, but this is another story. Now, whatever we needed to complete our understanding of the processes, to calibrate, validate our models, or to feed the machine learning algorithms, that what we badly need is data. And like for Sherlock Holmes, data is the clay for our bricks, and we need it throughout every phase of our coastal resilience building. Be it the assessment of the present state, the planning of the response strategies, or the monitoring of the effects of the measures we implemented. And particularly when we deal with climate, we need long series, typically longer than 30 years, enabling us to capture multi-decadal oscillations and discriminate them from long-term trends related to climate. And this can be achieved from in-situ observations, of course. Here you see on the right-hand side our oceanographic tower that has been collecting directional wave data for more than 40 years now. But also, satellite data are now achieving, as also David showed, besides spatial coverage, also long duration over time. And we have seen how, in the case of altimeters, this was crucial for providing global and regional estimates of sea level rise. So the coastal landscape and in general transitional systems such as deltas, estuaries, and lagoons are the results of a combination of different processes. And among the most important ones, we have the sea level rise relative to the land, of course, and the transport of sediments, which in turn is controlled by waves, currents, including tides, and wind, in a complex pattern of causal loops and feedbacks. And some morphological elements, such as coastal dunes or tidal marshes, vegetation also plays a role in consolidating the sediments or preventing erosion. So landscape evolution is not just a complicated matter of physics, but also a matter of ecology. And like in a cooking recipe, a different balance of these ingredients tend to lead the coastal system toward a different configuration. And we can have a tidal lagoon, so guess who's this guy here, an estuary, a delta, or an eBay, or so this concept is very familiar for the Venetians, who have been thriving for centuries by actively engineering the evolution of their lagoon. So at first, the ingredients were unbalanced for the taste of the era toward an excess of sediment supply, which was progressively filling the lagoon, which was unacceptable because the lagoon was the very strategic power point of Venice. And so they diverted important rivers outside the lagoon. And so for centuries, they kept on putting in place a number of interventions trying to cope with the current needs, be for protections or just exploitation of their assets, such as the case of the 20th century groundwater extraction, which is responsible for a significant part of the change we have found in the painting by Francesco Guardi. And now, here we are on the Murazzi at Palestrina in the southern lagoon of Venice. This is a massive defense work put in place by the Venetians in the 18th century and represents a historical front line between the lagoon on the right, because we are looking southwards, and the sea on the left. Nowadays, the balance among the ingredients of the lagoon recipe is different from that of the 14th century. We have sediment supply from the mainland, which is close to zero, and local hydrodynamic conditions make the export of sediment to the sea exceed the import from the sea with a net loss of material. And so the available sediment is not sufficient to keep pace with the relative sea level rise. And the net result is toward a marinization of the system with a generalized erosion and a degradation of the landscape diversity. Now, environmental pressures and socio-economic instances face Venice with new challenges. At the end of the day, one could argue that this has been the story for centuries, but this time things are happening faster and the pressures are stronger. In 1966, with its exceptional high tide, Venice was one of the first places in the world to raise some awareness on the threats of rising sea level. Today, the MOSE, which is the quite famous mobile barrier system conceived in the 80s, so 40 years ago, to protect Venice against the sea, is starting its operation. And for now, the risk of flooding is more or less under control, at least for a while. But the story doesn't end here. First, some new solution will have to be found before the sea level rises above the 60 centimeters threshold assumed in the design phase for, say, reasonable operability of the barriers. And this, we have seen, could be before the end of this century. And then there are some strategic and management aspects. It has been estimated with by a colleague of ours, by the way, that with a sea level rise of 50 centimeters, the barriers will have to be closed on average once a day in order to warrant the hydraulic safety of Venice. And this has implications for water quality, because Venice doesn't have a real sewage system. And as recently discovered by colleagues from the University of Padua, also possible implications for water quality, for landscape erosion. And last but not least, implications for marine traffic, because Venice is still a maritime city. But while centuries ago the ships at the base of the Venetian wealth were this size, now the lagoon is crossed by ships this size. And again, colleagues from my institution have shown that in some sheltered areas, and this is not only the case of lagoons, but also estuaries or coastal seas, the energy introduced by ship waves can largely dominate the coastal morphodynamics. So now the debate on both the Mose and the marine traffic in Venice and its lagoon highlights competing instances such as economic development against environmental conservation, and of protection priorities for the lagoon and its ecosystem against the protection priority for the city. So, although unique in the specificity of its issue, the case of Venice is representative of a common destiny putting together cities from the coast all over the world. That is, that the combined effect of the climate crisis and intensifying socioeconomic pressures requires an unprecedented effort to put together engineering solutions, economics, and social sciences into new integrated management paradigms. And well, I think we can do it. We only need to be faster than the rising tide. So if this is where we are headed, here is my best wish. Thank you very much.
Thank you, David. Thank you very much. You know, I wonder, these engineering solutions to sea level rise often have unintended consequences, of use you've indicated, particularly in Venice. And many adaptation strategies involve these structural initiatives and in some cases moving an entire town, but you're not going to move Venice, right? So the question is, has Italy focused attention on ecological as opposed to structural changes? I mean, this is going on in a lot of places. Structural changes are permanent. They're not flexible in any particular way. And there's this growing appreciation of ecological measures. Have these been considered in a serious way in Italy?
Well, from the engineering point of view, as far as I know, there are several branches of research that are focusing on the so-called working with nature paradigm. And Italy, and particularly I talk about the scientific and technical community is quite active in this. And also there are increasing efforts to share experiences and knowledge with other countries. So maybe referring to projects or activities dealing with similar coastal systems. So trying to understand to what extent an initiative is replicable and transferable, and what, of course, must be adapted to the specific issue of a coastal region or urban area.
Right.
So,
thank you, David. I'm sure we're going to return to this in the discussion that we'll have after all the talks have completed. Thank you very much, Davide. Let's move to our next. Let's move to our next speaker now. Melina Kourantidou is an environmental and resource economist who working particularly with marine resource management and governance, and she has experience both in and out of academia, and so she probably has quite a unique perspective. Her research combines both natural and social science research to analyze the effects of changes in coastal communities. So I think, but let me not prejudge, Melina will sort of expand our discussion from science that we've heard about to the policy and economic dimensions of coastal erosion, things that Davide has just touched on, including a summary of sort of adaptation strategies that will broaden our discussion of the spectrum of strategies that exist in an environment, in a variety of environments around the globe. Melina, we look forward to hearing your talk. Melina, you may be muted. I don't hear you. Is it possible that you've muted your... Do others, I'm not sure if it's my problem or yours, Melina. Do others hear Melina?
I can't hear either.
Okay. Melina, perhaps we could move on to Svenja's talk and come back while you deal with these technical issues, or it's possible when this happens to me, I often sign off and get back on, make sure my audio's on. Where we still cannot hear you. So let's move to Svenja's talk. Svenja, can you hear me?
Yes, I can hear you, and you can hopefully hear me.
Okay, yes, I can hear you as well. And we'll let Melina, we'll figure out the issue with Melina's audio, and we'll start. So, Svenja, I think you're very close by at the Woodhull Oceanographic Institute in Cape Cod. She studied I have particular interest in this talk because she studies the impacts of extreme temperature effects on a variety of coastal issues, right? After completing her doctorate in oceanography at the University of Bremen, where she studied, this is a problem I've looked at as well, the transport of warm water to one of the largest Antarctic ice shelves, which will be a factor in destabilizing the ice sheet behind it. I think that this talk will focus a little, we'll change our focus a little and discuss work on human-induced ocean warming and the implications of what seem to be accelerating trends on ecosystems in general. And I know of your work with fisheries in particular, Svenja. So I look forward to hearing your talk.
Okay, let me share my screen. All right, that works, yeah?
Yes, yes.
Okay, so yeah, thank you very much for having me. It's a little bit a different focus than the previous talks, and I'll hope to give you some insights on marine heat waves, which are these temperature extreme events in the ocean, and I'll focus on the Northeast US continental shelf. And bridging this gap or making the connection to the impacts and talking to coastal communities is really something that I'm starting to get into, because I think this work demonstrates and how important it is to make our science applicable. So it'll be a huge challenge for me in the future to really produce science that is directly relevant for our social communities. So I would like to give a shout out to a few people that I've been working with, Glenn Gewokowitz and Caroline Ummenhofer here at HUI, and German colleagues, Henrik Lindemann, who's actually a student that has been working with me on this project, and Anne Biasdorf and Torka Martin. And I hope by now these beautiful pieces of art have caught your eye. And these stem from an ongoing art science collaboration with one of the local artists who is based in Dartmouth, Massachusetts. And we've been working with her to kind of communicate, first of all, what are marine heat waves, what impacts can they have, but also our progress of work. How do we work? We use coding, we have to visualize our data, and I'll come back to these images throughout the talk. So Jerry already has given this brief introduction, so I'll just jump over it a little bit. So I did my bachelor's and master's in climate science in Kiel, Germany, and then moved to the Polar Institute based in Bremerhaven, where I did my PhD, which brought me to Antarctica multiple times. And I mostly used observational tools to study the warm water transport to one of the largest ice shelves, which, as Jerry said, is an important process for the potential destabilization of these ice sheets and ultimately the global sea level rise. And for my postdoctoral research, I went to the Warsaw Oceanographic Institution in 2019 with the Alexander von Humboldt Fellowship from Germany. And I've mostly been using computer simulations to try and understand these temperature extreme events, and in particular, the depth structure, something that we cannot observe with satellites. But let's start with what we can observe from satellites. And this goes in the direction from Davide earlier. So since the beginning of the 80s, we can observe the global ocean surface with satellites quite well. So we have an almost global coverage. And this shows the global average sea surface temperatures, which have been more or less with some variability, but they've been more or less rising constantly on a global average. And I'll come back to how important local aspects are as well. But first of all, let's look at the spatial distribution of this temperature change, so the trend throughout the last decades. We again see, similar to sea level, almost the whole ocean is warming up. So everything that is red has been warming, and patches that are even redder, such as the Northwest Atlantic, have been warming even faster than other places. And there's only few regions that have slight cooling trends. And you can imagine with these ongoing warm temperatures, we reach more and more extreme stages, and they will have strong impacts on the ecosystem and our coastal communities. And they're also actually linked to sea level rise that we see and parts in certain regions. But what is a marine heat wave? So we can start thinking about stationary climate, which means we don't have a trend in our data. We just have some variability about a mean. And we will have phases where we have warmer temperatures than average, and we have phases that are cooler temperatures than average. And the ecosystem has adjusted to this kind of variability over a long period of time. So for example, if we have fish that are migratory, if temperatures become a little bit extreme for short periods of time, so they exceed a certain threshold, these fish can just move away a little bit into different waters that are more suitable for them. Or seagrass has a mechanism to slow their growth and save some energy to survive these extreme events. However, in a warming climate, the temperatures exceed this threshold that we use to characterize extreme events more frequently for a longer period of time, and the overall temperatures are becoming more extremes. And this is when we talk about marine heat waves. So the discrete, prolonged, and enormously warm events that'll have substantial impacts on the ecosystem. And this is again some artwork from that highlights just certain species that have been impacted in off the Northeast US coast, such as squid, lobster, and in other regions in the ocean, kelp forest has been hugely impacted, and these garfish. So let's look at marine heat waves on a global scale. And this map shows several marine heat waves that have been shown to have drastic ecological, but also socioeconomic impacts. And you can see they're everywhere, and they're mostly, or often, we can find them along the coast. And two regions that I want to highlight that I've been working with is first the coast of Western Australia, which experienced a record marine heat wave in 2011. And this heat wave actually wiped out over 100 kilometers along the coast of kelp forest and changed it into a seaweed turf dominated region. And up to now, it seems like this has been a permanent ecosystem shift. And this came along with huge changes for the fishing industry. So multiple fisheries for scallops, abalone, they actually had to shut down because the condition changed after this event. But let's move to the Northwest Atlantic. So in 2012, they were kind of surprised by what is up to now still a record marine heat wave, and they really weren't prepared for such extreme temperatures. So what happened is that early in the year, what we can see in the top, we have a 30-year average here in the blue line, and on the gray line shows us the actual temperatures in 2012. So early in the year, the temperatures were already above normal. And what happened is that the lobster, what we see in the top, they started to land early in the region because the temperatures were so warm. So the lobster were like, oh yeah, let's get ready, and we're moving on shore. So what happened is that there was this early onset of lobster landings and an overall huge influx of lobster that year. And the industry was simply not prepared for such a huge influx. And it essentially led to a breakdown of the supply chain, and ultimately even to economic tensions between the US and Canada. And overall, this event resulted in a 38 million US dollar loss in the lobster fisheries. And coming back to local, to the point that we need to understand local changes and local variability, I want to give you a few insights on the ocean circulation and general processes that are important when we think about the coast of the Northeast US. So I would assume that the majority of people here know about the Gulf Stream. It's transporting, it's a huge, strong current that's transporting warm subtropical waters northward into the North Atlantic. So it follows the coast for a while and then actually detaches near Cape Hatteras and transports this heat into the interior Atlantic Ocean and all the way up to Europe. And it's actually responsible for the mild climate that we have in Europe. And what you can also see, but I'll highlight it, another important factor is we have also the influence of these colder and fresher waters that originate from the Arctic. And they're a key driver, or they're the main reason why the ecosystem of the coast here is so productive, because they provide oxygen, they provide nutrients, and really allow the ecosystem to thrive. But what is happening is that we see more and more warm temperatures in the region, particularly in the last decade. And so this is a time series in the Gulf of Maine, which is this region. Well, I hope you can see my pointer. Which is this region here. Cape Cod is here where we're based, Boston is here. And the Gulf of Maine has for a long time kind of varied, or the temperatures in the Gulf of Maine have for a long time varied around the global mean, following the mean increase. But since around 2010, there's actually an accelerated warming observed, similar to the sea level rise. And just to draw your attention to the year again, 2012 is when we saw this first marine heat wave. And ever since, actually, the region has experienced multiple marine heat waves. But it's not just the ocean that is warming, also the land is actually a warming hotspot when we look at the temperature change over the US. So it's really New England that has been experiencing temperature changes for up to 2 or 2.5 degrees since 1895. And there are studies, or it is our challenge to really connect these temperature changes that we see And there are studies that show that the warming ocean is actually an important contributor to this warming over land. There's also other processes such as changes in the atmospheric jet stream that can lead to these warming temperatures that we see over land. And this is also an important factor for changes that we see in Europe. So the atmospheric jet stream, similar to the Gulf Stream in the ocean, is separating cold polar air from warm tropical air. And for the marine heat wave in 2012, so here you see the sea surface temperature anomaly based on satellite data, and we see it's really this large spread warming in 2012. And what happened, this is shown based on observations, is that this jet stream moved further north and allowed more warm air to flow into the region, and actually led to a heat flux into the surface ocean. So we had this large scale warming of the ocean. Another process, though, that is also very important, and that brings us back to a regional point, is the pinch-off of warm core rings from the Gulf Stream. So the Gulf Stream starts to meander, so it becomes unstable and is generating these anticyclonic rings, which we call warm core rings, and they propagate actually to the west and bring these warmer and warmer tropical waters onto the continental shelf. And this is really a key process that we need to understand, because they bring a whole lot of different species into the region as well. And we've been working with fishermen that observe much more squid and other tropical species when one of these warm core rings come into the coastal region. So it's not just understanding the large-scale trend or the trend imposed by human work, but we really need to understand the local dynamics in the ocean and the atmosphere. And so for ecosystem assessments, it's important that we can also understand what's going on underneath the surface. And this is where we cannot use satellites anymore. We have developed a fantastic tool or fleet of observational tools throughout the last decade. So we can use traditionally ships and ship-based measurements, but we also have autonomous instruments such as Argo floats, gliders, or even marine mammals that collect data for us. But still, the subsurface observations are sparse in space and time, which is why we're using computer simulations that enable us to look at the dynamics in a more complex way, and also to look back in time. And a key factor about this region is that climate models often don't have the spatial resolution to resolve these important regional processes, such as the generation of warm core rings or the exchange between the Gulf Stream and the coastal waters. But we're using a high-resolution ocean model that is starting to capture these processes. So I just want to briefly show you a couple of results that we've been doing. So we were trying to kind of categorize marine heat waves, so these temperature extreme events, and find different types of events. And one example is in 2002. So this is the temperature that is averaged over the continental shelf. And we can now, with the model, actually look also what's happening at depth. And we can see that early in the year, these temperature anomalies started to evolve on the surface, and everything that is dotted with these black dots is a marine heat wave, or is a marine heat wave state. So the temperatures exceed this threshold that we derive. And we can see it really throughout the whole year. We have almost an ongoing marine heat wave there, but it's really limited to the upper 30 meters. Which means it's based at the surface and doesn't reach the full depth. When we look at the spatial distribution of this marine heat wave, so everything that is red, or the redder it is, means that the more of the water column, a higher percentage of the water column is a marine heat wave state. So we see that actually closer to the coast, where we have shallow seas that are only 30, 40 meters high, deep, we have a marine the marine heat wave occupies the whole water column, but it doesn't really reach to the outer shelf of the edge. And by the way, this is Cape Cod here and New York, so this is the mid-Atlantic bight. But now we're coming back to these warm core rings that are impinging on the continental shelf. And this is that they can drive a different kind of marine heat wave. And this is an example from 2014, where we really see these subsurface intensified temperature anomalies, and the temperatures reach up to 6 degrees Celsius above normal. So there are huge temperature differences that will impact the fish in the region and the fish distribution. When we look at the spatial distribution here, we see that these are really only focused on the outer shelf, and the inner shelf is not impacted as much, but we see a lot of activity in the slope region. And we can animate this and actually see how the model is capable of producing these warm core rings that bring in the warm water and advect it along the continental slope. Another point that Davide made is we need data. And we need to be able to look back in time to understand these multi-decadal variations that can potentially superimpose warming trends or anthropogenically forced warming trends. So what the model allows us, this is again is the shelf the temperature averaged over the shelf, and we can go back to 1960. And these are temperature anomalies, and we can see that there are warm-up periods, such as here in the late 70s and early 80s, and then there's colder periods where we hardly see any marine heat waves there. And then in 2012, again, 2010, the ocean seems to change again, and we're entering a phase of warm anomalies. And so when we go back to our time series from the warming Gulf of Maine, which is based on surface observations, we do see the strong increase starting around 2010. But we now see in the model that this is not just a surface temperature increase, but it seems like it's a whole regime shift within the ocean. So also the subsurface ocean is changing. And there's other studies that have looked at these patterns of variability in the North Atlantic, and they find kind of a dipole mode structure that says when the coast of the US is warm and saline, the Northeast Atlantic, so the coast of front of Europe, is fresher and colder. And this dipole changes changes its sign on a multi-decadal time scale. And again, we only started to have satellite observations in the 80s, so we're only really capturing this cold period following by a warm period, but we need to understand how this variability plays or fits into the large trends that we see. And okay, I'm gonna come to my last two slides. Coming to the impacts for fisheries. So we're working closely with the Commercial Fisheries Research Foundation, where we have regular exchange with the fishermen directly. So we inform them of the changes that we see, the processes that are important for them. And they actually, as part of this project, deploy their own oceanographic measurements that allows them to see the vertical structure of temperature in the ocean, because as I said, these warm core rings, they bring completely different species that they might not be after into the region. And they're really keen now to deploy these instruments because it's helped them with their fishing efforts. But it's really a two-way street. So they're collecting data for us, data that is very valuable, that we otherwise wouldn't have. And so this program has been going since 2015. They collected around 750 profiles in that time, and that really allows us to look at interannual variability at depth on the shelf. And finally, I think a challenge for us in the future is really to communicate our science to a broader audience. And this brings me back to this art-science collaboration that has been really rewarding, and I think really can speak to the public, and we'll have multiple exhibitions planned throughout this year and next year. And we really captured a lot of aspects of our work. So impacts of the marine heat waves on various species, but also how we work. We need a lot of data. We can use satellites, we can use oceanographic instruments. Then we need powerful computers, and where we code, read in our data and visualize our data. And then we get results that we need to interpret. So Deb Ahrens came up with these 3D marine heat wave panels, 5 of them. Their pattern is motivated by the warm core rings that spin and transport these warm waters. And I think they're really a fantastic way to communicate our science. So to end up, the Northeast US land and ocean are experiencing drastic changes that drive an accelerated warming and extreme events. And again, to highlight the point, we need to understand local processes. We cannot just talk about global means. We need to understand the variability that is superimposed on the mean trend that's anthropogenically forced. And this will also inform us of processes that climate models maybe are not able to that climate models are not able to capture yet, but that are really important to understand or to do projections in the future. Marine heat waves are not only a stress test for the ocean's ecosystem, but also for millions of people who rely on them. So it's really not just the physical components, but biological components and societal components that we now need to bring together and start a conversation. Collaborations with stakeholders important, and it's really a two-way street. We both parties profit from that. And we need to find ways to communicate our science and more broadly, the implications of changing climate to a broader audience. Thank you. And sorry for going over time.
No, that's great, Svenja. Thank you for this. And your take-home messages, I hope we'll return to at the end in our broader discussion. I wonder to what extent you feel these heat events will be predictable in the future. It seems to me, I mean, these are major events. Your 6 degrees Celsius is the difference between mean atmospheric temperature at the depths of the ice age and into the glacial. So it's really a shocking change. And I wonder, can we predict them? What's the prognosis for predicting them?
Yeah, it's tough. I think it's kind of a mixture of predicting these individual events, these rings that are kind of intrinsic variability of the Gulf Stream. It's hard to predict when a ring will really form, but they have a time scale from when they form and actually hit the shelf. It's several months. So we are able to look out for these features and track them with the satellite. And when we know what kind of implications they can have on the shelf, we can give the fishermen, for example, a heads up and say there's a huge ring forming, and this is what we're actually doing. My advisor, he will call the Commercial Fisheries Research Foundation and say there's a ring forming, keep an eye out. And the fishermen are getting to the point where they understand these processes and what implications it has. And this is a process that acts on top of this large-scale regime shift. So, you know, a marine heat wave is in the end only a statistical construct. And if I have a whole regime shift to a much warmer regime, I will ultimately, when I form one of these warm core rings, have a marine heat wave there. So, yeah, I think predicting is tough, but we can look for indicators that allow a couple of months heads up of what might be coming.
Yeah, that's interesting. I mean, your discussion of your being an early warning system, it seems.
Exactly, yeah.
And you have a question in the chat from Jean-Philippe Nicolai, who asks, do we know the consequences of heat waves on whale migration routes along the Northeast coast?
I'm sure there's studies. I'm not an expert on that. I do know that, so NOAA, the National Oceanographic and Atmospheric Association, they actually come out with an ecosystem state report each year, and they do see changes in, for example, North Atlantic whales and how they've been declining since kind of this regime shift occurred in 2010. And certainly we do see different patterns of migration. For example, one of the Hui scientists, he started tagging whale sharks off the coast of Cape Cod last year, and there was a huge amount of whale sharks that have never been seen up here before. So that is an indication that the waters are much warmer, more tropical now, that allows these species to move forward or move further northward. But yeah, I don't know too many details that I could give now.
Well, thank you, Svenja. in the interest of time, I think we'll move on now to Melina's talk.
How is my sound now? Can you hear
We
me?
hear you loud and clear.
Okay, perfect.
So,
my apologies to everyone about my technical difficulties. Seems
No,
like
no.
2 years and the pandemic hasn't. Yeah.
well, as I said
Yes.
to you, what's a webinar without a technical glitch now and then? So, Melina, I think I introduced you, so why don't we start in right away, please?
Right, okay. Just let me share my screen here. Right, so yeah, hello everyone. My name is Melina Kourantidou, and before I get into the socioeconomic and policy dimensions of coastal erosion and sea level rise, let me say a couple of words about my background. I grew up close to the coast in the Mediterranean, and for my education as a scientist, I moved to Scandinavia, Denmark in specific, and became interested in marine policy and coastal communities. Then I moved to Canada and worked with marine policy and governance issues in the Canadian Arctic. And after that, I found myself in Woods Hole in Massachusetts, working for the Marine Policy Center at the Woods Hole Oceanographic Institution on topics related to the ocean and the coasts. I'm now affiliated with HOI as a guest investigator, and I'm physically in Brittany, in France, specifically in the city of Brest. Coastal zones are retreating globally, and there have been plenty of voices over several years recognizing the risks associated to floods and the choices of people that trigger costly reactions to disasters. But truly, the way I see this as an environmental and resource economist, the problem is very much of an economic problem. And even Adam Smith himself, more than 2 centuries ago, hinted on this particular problem. And when we think of the US, we don't really think of it as a coastal nation, is the truth. But indeed, as Jeffrey Sachs from the Earth Institute of Columbia University reminds us, there's an increasing relative demand for quality of life that comes from long-term rising incomes. And this serves as a force that should continue to concentrate US populations at the coast. And indeed, the numbers over time confirm this. Specifically, the size of the coastal shoreline and the coastal watershed counties and the people living in those. Essentially, it's the density of people on the coasts, which is rather high and at times worrisome. And here's a snapshot of some key US coastal demographics. It's worth noting that there's more than 300,000 homes and buildings located within just 500 feet of the ocean. And there's 85,000 homes in the so-called erosion hazard areas. And there's 1,500 homes lost to erosion every single year. And the costs of the shoreline change have been estimated somewhere between 1 to 8 billion per year. Now, where are these costs coming from? Shoreline change is triggering land erosion to buildings oftentimes, and overall can be very costly to coastal property owners. So there have been estimates that by mid-century, 25% of the property owners within 150 meters of the shoreline may be affected by property losses triggered by erosion. In my field, in environmental and resource economics, we use what we call hedonic pricing methods to assess these types of coastal hazard costs. And these methods essentially measure property values encompassing coastal amenities and recreational values. But on the optimistic side of things, there have also been estimates that about 70% of the US Atlantic coast is able to respond dynamically to sea level rise. And here's a list of some US institutions enhancing coastal persistence through their investments. The numbers you see on this table are in $1 million per year. And the costs are clearly very high, with subsidized national flood insurance premiums being at the top of this list. Now, how does one deal with erosion hazards? First of all, when presented with erosion hazards, people who live on the shoreline or near the shoreline can choose either to protect their properties through seawalls, beach replenishment, and so on, or to relocate further away from the coast. And then from a policy standpoint, research that contributes to information for making community decisions is of critical importance, as it can help those communities to choose whether or not to invest in coastal protection. And to be able to inform those decisions, it is important to be able to understand the coefficients of the environmental variables in these hedonic models that reflect the prices that the homeowners of the coastal properties are willing to pay to reduce the exposure of their properties to erosion risks. Yeah, and here I'm showing the results of one such relevant study a few years back from my colleagues at the Marine Policy Center, focused on 3 cities in Massachusetts, which is really has a complex coastline along which both erosion and accretion can occur. So basically, the main findings of the study was that an increase in the erosion rate of the nearest shoreline should have a negative effect on the sale price of a home, because a higher erosion rate may increase the probability of inundation, damage, and loss of property in future decades, particularly for the oceanfront residences. But then again, effects of erosion, elevation, and seawalls appear to be limited to properties located in close proximity to the water or to oceanfront residences. And specifically, the average marginal increase in nearshore property values associated with 1 meter in horizontal distance. Associated with 1 meter of decrease in the erosion rate is 0.2%. And now, of course, these types of analysis have come with limitations, and a lot of these limitations, as was discussed previously, have to do with the data itself. So the data on coastal hazard characterization, such as erosion and elevation, can be imprecise at times. There can be significant errors in coastal erosion measurements because of dynamic interactions between natural erosion and beach nourishment. And of course, there's space for future improvements to these hedonic modeling exercises that I mentioned for the coastal hazards, that because these need to depend on improvements in how we understand coastal geodynamic processes and coastal mapping. And over to coordination in coastal protection. Well, given a change in a natural coastal system, such as that caused by erosion, property owners choose either to retreat or to protect their properties in order to minimize the expected damages or maximize the property values, if you wish, for their planning horizons. However, coastal protection is often not coordinated, which can be a big problem. So there's the studies examining the net benefits of different alternative strategies to undertake either soft structural responses to erosion or decide alternatively. And in this case, property owners may either decide to respond independently or coordinate their individual responses. So that depends on the policy chosen. And the results can be significantly different, both in terms of geomorphic features and economic impacts. What we know, though, for sure, that is that uncoordinated responses are often ineffective in controlling erosion, and that can lead to severe economic losses of land and property. So the studies assessing the problem of coordination typically find that coordination is key to stabilize the shoreline and maximize the overall economic benefits. Now, here you can see a map of the Massachusetts coastline with the different erosion structures amounting to more than 3,700 structures. varying from seawalls and dune reconstructions, beach replenishment, and so on. As you can see, it's a busy coast filled with coastal structures that aim to protect the coast from erosion. Now, historically, public policies directed at the problem of coastal erosion in Massachusetts focused on options for modernizing or expanding coastal engineering structures, such as seawalls, revetments, or bulkheads to protect the built environment. Even though this has largely changed today, it is important to know that the hard structural protections can be not only costly, but also very short-term solutions. And when these types of protections tend to get destroyed from some extreme event, the cost to the federal and state governments can be significant. Now, one market-based complement to a rolling easement encompasses conservation easements, where governments and non-governmental organizations or local community groups could purchase any extant rights from a private landowner to construct hard or soft structural protection. Other options include, for example, a buyout through which the property could be purchased from its owner, or a buyout leaseback involving a property purchase and subsequent rental of the property back to its original owner or to another tenant. And there's been studies looking at how strong the different incentives are for the property owners to protect their properties. With public soft structures or on the ocean fronts affecting property values the most, as you can see in this table. Now, is coastal erosion always a challenge? Well, not if there's enough space and buffer zones. The challenges arise when coastal zones are highly urbanized and urbanization draws nearer to the shoreline. This makes the buildings and its residents more exposed to the possible damages from flooding and erosion. And actually, planned coastal defense constructions may aggravate erosion by trapping sediments. And so soft or hard structures can protect the individual properties and infrastructure from damage, allowing economic benefits of coastal living and tourism to continue to be realized. It is regular practice, for example, to be adding sediment to the berm dune system to increase beach width and dune height. I'll very briefly discuss the case of New Jersey, where highly valued development and infrastructure lay behind the berm dune systems. After the impact of Hurricane Sandy in October 2012, the state of New Jersey adopted large-scale engineered berm dune structures as their primarily coastal protection strategy. So that was large investments of more than $5 billion. With the estimated coastal and inland by Hurricane Sandy totaling more than $37 billion in damages, the U.S. Army Corps of Engineers found that the construction cost of these berm dunes was economically justified. It is unclear, however, if the resources exist to maintain these newly engineered landscapes, considering that there's a need to re-nourish the berm dunes every 7 years. So it should really be the communities answering those questions, but it is also the private owners' perceptions of risk property loss that matters in making these decisions. Now, an important line of research that my colleagues at the Marine Policy Center have been working on is to assess whether it is economically justifiable for beachfront communities to cover the costs associated with engineered berm dune systems in the long term. Answers to these questions can come from geoeconomic models that consist of a model of the morphodynamic evolution of the system that includes dune migration, beach and dune erosion, and renourishment of the beach and the dune, and also from economic models on the property owner's decisions to maintain the dune through nourishment. And that's where real estate market outcomes for coastal protection versus ocean views come into play. And there's this really nice paper published in Anthropocene and Coasts, published by my colleagues, and I'm happy to share a copy of that with whoever is interested. And let's take a look at what adaptation may look like. Those of you familiar with Cape Cod may be familiar with pictures on the bottom of the like the ones on the bottom of this slide. And well, one of the key questions that our field is trying to answer is this social optimal timing of actions, such as delaying, protecting, and ultimately abandoning. And it seems like the primary strategy across the Massachusetts coast is to protect. Adaptation has to do with the choice over the extent of protection. And for beachfront communities, this choice of adaptation may involve determining a target beach nourishment volume that would result in a beach that is wide enough to provide both protection and recreational amenities during a foreseeable period. And today we have much better data than we used to in the past. So coastal monitoring programs that allow us to measure the daily shoreline erosion and accretion, responses to storms, seasonal cycles, and other anthropogenic interventions such as beach nourishment. Then we also have great shoreline data to assess variability and vulnerability. And there's also a growing literature with geoeconomic analysis of coastal property values and beach nourishment and shoreline changes and so on and so forth. And then the important thing is to be able to understand the benefits of these structures, such as beach width, and the costs and benefits of the maintenance and how these relate to recreational uses. And then part of this work is also efforts to model private owners' strategies to control erosion through noticing fronting beach to identify the optimal beach width. So here you can see the Massachusetts erosion hotspots, and I'm going to close with briefly discussing the case of Plum Island. Coastal barrier systems around the world are experiencing high rates of flooding and shoreline erosion. So the case of Plum Island is yet another neat example of this type of study on the north shore of Massachusetts. So here my colleagues work to assess the factors that contribute to adaptation on Plum Island, which is a developed beach and dune system on the north shore of Massachusetts. So the case of adaptation here is particularly interesting in the face of episodic floods and fleeting erosion events, driven by a combination of strong northeast storms and cycles of erosion and accretion. What they found was that the value of the average residence on Plum Island was increasing by 34% for the ocean front properties. And despite all the state policies discouraging physical protection as a means of adaptation, coastal communities face political and financial pressures to maintain these existing protective structures or to allow all these other groups of property owners to build new ones through collective action. However, these factors mitigate against adapting to the shoreline change by retreating from the coast, thereby increasing the adverse effects of coastal hazards. Closing up, so the takeaway points are with respect to resilience, because a lot of this adaptation discussion is essentially about coastal resilience. So it has to do with being able to bounce back from a natural hazard, such as flooding, erosion, or property loss. The coastal environment has been built out really, and it's still expanding, which is a major risk factor. Economic incentives are aligned, and policies have been designed to protect these coastal properties, but not to abandon and retreat. And coastal communities have been observed to bounce back, but the question we should be seeking to answer is whether the net benefits what are the net benefits from protection. And I'll close with a couple of grim pictures from about 10 years ago here in Massachusetts. Thank you for your attention, and I will take any questions you have.
Thank you, Melina. I wonder, I'm interested, of course, in tipping points that occur for all of our speakers, and what would constitute a tipping point that would convince one to move from protection to abandonment? What governs that change, that decision, which is clearly an important decision and one with incredible impacts on humans. When are those decisions made? What governs that?
Is the question for me or for the panel?
Yeah, no, for you, Melina. And
okay.
We can broaden it, but when do people decide, or when is it decided for them that abandonment becomes the only option?
Well, it's a very good and hard question to answer.
Yes,
Tipping points is a very interesting way to approach this problem, as with many other conservation and adaptation problems. But really, the challenge here is the private properties and the ability of these people, of the private owners, to choose for themselves. So despite the costs incurred by state and federal governments, I mean, ideally, it's been shown by several studies that retreating the community is the safest and most economic option. Nevertheless, you cannot necessarily force people who are willing to pay to have their properties on the shoreline to retreat. And so we continue to invest in built infrastructure and maintaining this built infrastructure for protection, which is very, very costly.
Great, thank you very much. Maybe we could extend that question to the broader group. I'm interested, we're in this accelerating change of climate. When for each of you do you feel within the areas that you study, we will reach a point where some fundamental change will occur? Have any of you thought of that issue? I mean, one thing we should tell those who are listening is that we all know, all of us on this, that changing temperatures 1 degree instead of a ½ degree doesn't just double the impact. There is a nonlinearity there. And what are the thresholds that you worry about in particular in your research?
Clearly, for climate research on sea level rise, something which is very frequently said is that, of course, there are tipping points around the fate of the West Antarctic ice sheet. Clearly, but well, still, that's a big open question. We don't know where the tipping point is exactly in terms of global warming. Is it at +2 degrees sustained, or 3? I think this is currently unknown. Well, personally, that's why I'm very much interested in ice sheets, and especially coupling ice sheet models for more interactivity in our climate models. That's my that's my goal currently.
Yeah, and I guess, Davide, I would add that it's probably also governs your interest. And people sometimes ask me, why do I study the last interglacial? And I say, because we look there for evidence of tipping points and for collapse of ice sheets and wonder what were the conditions necessary to produce that collapse. Svenja, you were going, I think, to say something about tipping points.
Yeah, I think, from a community perspective, unfortunately, people tend to be very reluctant until they're directly impacted and see the changes by themselves. If house owners, if their house is being washed away multiple times, maybe at some point they realize staying is not an option. Same, people that are mountaineering, going to glaciers, and they see firsthand how the environment has been changing. Fisheries communities, they see the changes happening, and you can see how, with the interactions that we have, how needy or how interested they are in learning what they can do different. And ultimately they depend on government changes, of course, because they're regulated by governmental rules as well. But yeah, I think these large, these global tipping points, such as will the West Antarctic ice sheets collapse, these are important questions that we can address with climate models that we need to address. But I think first we need to convince people that change is happening and give them a chance to relate to something that they care about, whether that's on a personal level or on a local community level.
Well, I guess that raises in my mind another question. You talked about art, and that is, how do we improve public engagement in what we do. It's a kind of central issue for me. I have a brother who's a journalist, and he said that most stories have 2 or 3 day shelf life. And we have images of the West Antarctic ice shelves, and 3 or 4 days later, we're on to the other, obvious issue that takes our attention. How might we as climate scientists, social scientists and climate scientists improve sort of public engagement in this? I have found it difficult to keep people's attention on these issues. What do people think? David?
Well, yeah, I've discussed that as well with journalists, and it raises lots of questions. Sometimes I talk to the grand public, and since basically I'm a sea ice modeler, I used to show a polar bear on a sea ice flow, and I realized this is not a good idea to talk to French people, because they say, well, that's far away, that's really a pity for the Arctic ecosystem. But really, I realized that it's to talk to the people here in France is perhaps better to show the consequences of climate change in their cities for French agriculture. Well, I realized that, and also trying to speak in a different way. The IPCC tries that as well. For example, instead of presenting a climate emission scenario, and I did that just 1 hour ago, and show how sea level will be, perhaps show, make comparisons with previous events. In France, our reference heat wave is 2003, and well, things that work is to show that under quite high emission scenario, the summer we had in 2003 might be the normal summer in 2100. But 2100 is perhaps not a good idea either, because people say it's really far, and that's for our grandchildren, and they don't always feel very much concerned about that. So I think there should be some constant thinking about how to communicate the best way, and talk to the people, see what works or what doesn't work. And we need the social sciences to do so. I'm very, very convinced of that.
It's hard to convince the public sometimes when they see this problem as something that is distant from them. That's certainly true. I had a debate once with an economist, and the issue of cost, I mean, this goes to Melina's talk on sort of one of the best ways to have people pay attention is to realize that their property values are going down, but it's not necessarily the most global way of dealing with these impacts. Svenja, how has your art component of your work been taken up by the public?
I mean, unfortunately, we didn't have, since COVID and the pandemic happened, we didn't have too many in-person public events. But I feel like that it's taken up very well, and our plan is to provide more educational material along with that, so that when people can see a satellite or a certain creature on these panels, that they have resources to go to, that it give them more information, and maybe bring that into schools, develop educational tools that can be used for school projects. But yeah, as you say, it's really tough, and I'm only at the beginning of my scientific career, so for me it's really a challenge of doing my research but still feeling that urge to having to communicate in an efficient way. So one of these, I think things like this art collaboration are a great way to engage the local community, at least, and make them aware of what's going, what changes are happening right in front of their doorstep. As you said, David, showing changes in the Antarctic ice coverage, or thickness. People cannot relate to that. And that's the issue that I had during my PhD is like, of course, it's an important issue to study the warm water transport of the ice shelves, but they're like, why do I care? It's like 100 years away. So finding something that they relate to, I think, like you said, remember the summer in 2003, everyone complained it was crazy hot. We had death, we had lots of issues. Try to compare it to events that people can relate to, I think is a key.
We are reaching a point where there's always this question we must all receive about the difference between weather and climate. But
yeah.
We are reaching, those of us my age are reaching a point where we can look back and say, winter, I'm Canadian, and winter in Toronto when I was a young boy was very different from winter today. One would have to have not only a shovel, but an ice pick in Toronto in the early 1970s. And one doesn't need an ice pick anymore in Toronto generally, except for these extreme climate events. Dr. Bonaldo, you had something, you had your hand up. David, yeah, you have your hand.
Yeah, thanks. So do you hear me?
Yes.
Okay. Yeah, so thanks. For our experience, mine and my colleagues, we have found that one strategy that can bridge, if not the geographical gap, but at least the temporal one, is showing that the physics is actually there to have catastrophic events even now, even without climate change. And we have an interesting example for Venice. Yeah. And the 1966 storm, which I mentioned before, which is the Acqua Granda, the big water called in Venice, was 192 centimeters above the historical reference, and it was catastrophic. As you know, the sea level in Venice is the result of several factors. There is the astronomic tide, the meteorological tide, which is a storm surge, and there is the resonance of the internal resonance of the Adriatic basin, and then there are atmospheric pressures. Some colleagues have, and so the timing in this is crucial, and some colleagues have tried to analyze the historical storms, decomposing all the components of the sea level for those storms, and they have found out that if all the factors in present condition come simultaneously, so full moon, maximum tidal maximum, synchronized with the Adriatic Sea and synchronized with the passage of the pressure minimum, the maximum level in the lagoon could exceed 210 centimeters, which means almost 100% of the city flooded. So, and this is something that typically, if you tell them to Venetians, they're not aware of this. They say, well, they used to think that the 1966 event was exceptional. They have started changing their ideas with the event of the 2019, which were just 5 centimeters below. But still, there's not full awareness of the fact that physics is already there, and it's just a matter of statistics. So I think that this could apply also for other coastal systems, where if things have not yet gone terribly wrong, just because of chance and not because climate change is very far away.
Mm-hmm.
Yeah, where sometimes there are so many examples of these so-called perfect storms, a convergence of a number of factors that lead to these extreme events that raise public awareness. We're sometimes, as climate change scientists and social scientists, accused of being pessimists. I don't think I am, because I see probably my source of optimism is watching young people my nieces protesting on the streets, demanding change in a way that probably wasn't, well, certainly wasn't true 10 or 15 years ago. And I think for all of us, that's a source of optimism. It is, at least for me, within this sea of bad news, as we say. So I think we've reached out the end of our time. I want to thank the organizers again, and of course to the 4 speakers today. I think the diversity that you show in location is a good reflection of emphasizing the global nature of this problem and the requirement for global solutions. I hope those who attended learned as much as I did today. I have copious notes that I'm going to follow up on after this to read up on some of these issues. So I wish everyone a good afternoon, and I hope they go out. In Cambridge, Massachusetts, we have a beautiful day. I hope everyone has a beautiful day close to them. They can go out to enjoy this earth of ours, but also to appreciate a little bit more because of your talks of fragility that we worry so much about. So thank you very much to the speakers again, and thank you to the French consulate for the organization. I wish you all a great afternoon.
Thank you.
Thank you.
Thank you very much.
Thank you.
It's
Bye-bye.
great to talk with you.
Have a good day.
Bye-bye.
Bye.